John Crow.
Welcome. It's nice to see some familiar faces from yesterday's Intro to Deep Learning session. This is a more advanced session. We'll get into that in a bit more detail. This is my puppy Obo. He's the mascot for the series. And yes, we're here for a session on natural language processing with GPT-4 and other large language models. We'll be covering training all the way through to deployment with the key models for abstracting away doing that, which are the Hugging Face Transformers library and PyTorch Lightning. So you can go to my website, johncrone.com/talks, and you can go to today's date, which is May 10th. And then there are slides for today, as well as the GitHub repo for today. So let's actually get right into a hands-on demo right off the bat, because people love hands-on demos. So I've got our first demo is here in the repo. There's a code directory, which is full of Jupyter notebooks as well as some Python files. We'll get to those Python files right at the end of this session. So the very first notebook that we want is this GPT-4, it's the GPT-4all inference. So this notebook here, it's very simple. Just to give you a taste of how you can get these powerful LLMs on your own device. So with all of my Jupyter notebooks in this repo, you can click on Open in Colab. And I've tested them all. They will work. Once you're in Colab, you can go to Edit, Clear All Outputs, so that the outputs that are saved from me already having previously run this, disappear. And then it's gonna take a while to run these first couple steps. So thankfully, these aren't downloading onto your local device. So while we are all log jamming on the Wi-Fi, at least the enormous LLM that's currently being downloaded is happening in a remote server. And so, yeah, so we'll come back to this in a moment, but you should see that this will work well and you can adapt. Hopefully this is all pretty obvious. It's a very nice and slick API. It's actually running on the CPU of this device using something called quantizing, which we'll get into later. And I'll also get into detail on this GPT-4all algorithm. But the Cole's notes is that it's a large language model that fits onto a single machine and allows you to have GPT-4 or at least GPT 3.5-like capabilities in being able to interpret your instructions and have a real conversation with you. So I've got it kicking off with, please answer this question. What is a large language model? While that is booting up, feel free to, maybe on your phone instead of on your desktop computer, do feel free to connect with me. So I have an email newsletter on my website, johncrone.com, to make sure you don't miss any updates. And I have almost all of my content is free. Feel free to connect with me on LinkedIn. Just mention specifically that ODSC East. Just say ODSC East somewhere in the connection request. Otherwise, there's too many of them for me to say yes to all of them. I have a YouTube channel with lots of free YouTube videos and a Twitter account, and I host Super Data Science, which is the most listened to podcast in the data science industry. We have 2 episodes a week, every week of the year, with the latest information on machine learning, AI, data career success, and lots of amazing guests. And then the question here is, what is your level of experience with the topic? So little to no exposure to deep learning. We've got a few of those, although some of those people were in my deep learning class yesterday. I'm sorry that I didn't teach very well. Some deep learning theory, nice. Some deep learning theory and experience with the deep learning library. All right, we got more hands going up. And strong deep learning experience. Okay, so large language models do depend on deep learning. We're not going to be doing any math related to deep learning or any math related to machine learning at all. We're going to be using high-level abstraction tools, but sometimes I will be using terminology like epochs and batches that I'm not going to take the time to explain because I'm assuming that you have that knowledge. If some of the terms that I used today move too quickly for you, I've got a book called Deep Learning Illustrated. So very special thanks. This content in today's session, a lot of it is influenced directly by a session that I did in the O'Reilly platform last month, which was a live conference on large language models. And so the three presenters from that were hugely influential on the content that I have in here. So that's Melanie Subaya, who's one of the first authors on the OpenAI GPT-3 paper. Sinan Ozdemir, you'll see lots of his code in today's session. He's an amazing instructor on large language models. I'll be providing with more resources of his later on. And emboldened, Sean Kosla, who's here in person. He's a data scientist on my team, and he was hugely helpful in creating a lot of the code that we're going to be running today. So thank you, Sean. All right, so in this, we have 4 sections that we're going to go through. I'm going to introduce what large language models are. Then we're going to go over the breadth of large language model capabilities. I will then teach you how to train and deploy large language models. And finally, in the 4th section, relatively quick one, on getting commercial value from LLMs. So this isn't just technical. We're going to have some stuff at the end on how you can be making a big impact with these really incredible capabilities. All right, we're going to start with the intro, of course. So, a brief history of natural language processing. Prehistory in natural language processing was neural net free. So we've had techniques like this since the 50s, bag of words approaches, TF-IDF, topic models like latent Dirichlet allocation. The Bronze Age actually happened relatively recently. So just 10 years ago, the Bronze Age kicked off in NLP. So this was when we started having language embeddings like Word2Vec, and we started using those language embeddings and flowing them through deep neural networks like RNNs, including RNN subtypes like LSTMs, gated recurrent units, and we mapped those language embeddings, often word embeddings, through to some outcome that we are trying to predict. And that worked pretty well. The Bronze Age was a big improvement over prehistory. The Iron Age is really recent. So this is when we started having large language models with attention. The transformer, which I'm going to go into more detail on shortly, was devised in just 2017, so 6 years ago. And it made its way into a lot of really famous architectures for large language model architectures for natural language processing in recent years. Architectures like BERT, T5, and GPT-3, all of which I will be talking about in more detail in the coming slides. But the approach that set about the industrial revolution that we are in the midst of right now, that is transforming our industry as well as transforming all industries over the world, was facilitated by RLHF, reinforcement learning from human feedback. This is what has allowed, through InstructGPT early last year, early 2022, and then through the ChatGPT user interface that had some more guardrails around the InstructGPT interface. It's this RLHF that has aligned this machine's outputs with uncannily what you were anticipating. And a huge amount of human work has gone into making that happening with respect to labeling data, so labeling instruction and response pairs, and allowing that to be so well aligned with the kinds of things that you'd like to be seeing. In March of this year, GPT-4 came out, which is a step change on this RLHF approach. And if you haven't used GPT-4, you've got to. I couldn't possibly have made this presentation on the timeline that I did without GPT-4. I'm talking about the code. I'm talking about topic summaries. I was able to come up with ways of, I'd run into problems in my code, errors. I'd try to Google things and would spend 10 minutes, 15 minutes trying to find the answer in documentation, and then just throw my hands up and say, I know GPT-4 hasn't been updated since September 2021, but I got to give it a shot with this new PyTorch Lightning library anyway. And I should have just started there, because I could paste my code in and it would fix my code to do exactly what I wanted to do. Not arbitrary code from the internet that's like my example, literally my example, and it runs perfectly. So this GPT-4 architecture is a huge step change. I'm going to talk about it a lot in this training. And other companies other than OpenAI like Anthropic and Cohere also have models of GPT-4's complexity that will be available in the public soon. So transformers are what have enabled the Iron Age. So attention was being used in the Bronze Age. So attention, which transformers do, is this concept that we've had since having deep neural networks applied to NLP. And attention is this idea of being able to look over long stretches of language to get relevant context. And this is something that we do as humans when we're thinking about what sentence we're going to say or how we're going to communicate with somebody else. So this was key. The innovation with the transformer and why it ushered in the Iron Age is that we discovered that attention is all you need. And that's the name of the Vaswani et al. Paper from 2017. So for natural language processing, deep neural networks, apparently all we need is attention. So the architectures previously, they still included recurrent layers, they still included convolutional layers, whereas now today, our architectures are transformers only. Attention is all you need. What is a transformer? We don't have time to go into a huge amount of detail on it, but broadly, it follows this structure that you see here. So you have inputs, and those inputs get encoded into a feature layer. So you have these abstracted embeddings in this feature layer, and then those embeddings can be decoded, and you get some outputs. So the first transformer paper from 2017 from the Google Brain team, that was neural machine translation. So let's have a look at an example here. So if you have English going in as an input, hello world, that can be encoded by the transformer. It gets converted into these embeddings in the feature layer, and then those can be decoded and output in the language of your choice, say French, and we can have bonjour le monde. So we can't go into a huge amount of detail on the transformer. I could spend 3 hours doing that, but some great resources are here in my slides, including the annotated transformer and the illustrated transformer. Key to our understanding of how transformers work and how modern NLP works in general is the idea of subword tokenization. So in natural language processing, a token is the currency. So it's a basic unit of text. And these tokens are processed or extracted from your corpus, which is Latin for body. It's your full body of language that you're working with. And there's a range of possible levels for these tokens. You can have sentence level tokens, so breaking on a period or exclamation marks and question marks to have big sentence level tokens. Much more common is word level tokens, where you're breaking up on white space and punctuation so that you have each token corresponding to a word. But modern transformers tend to either use character level or, even more commonly, subword level. So what does that mean, subword? Well, I have an example here. We have unfriendly. And so that could be broken up into potentially 3 subwords, where friend is one of them, friendly, and un at the front, is a negation. And so altogether, this means that even if our algorithm had never come across the word unfriendly in its training data, but it had come across the parts un and friend and ly, it could combine those together to understand this new word. So this gives modern NLP algorithms an enormous amount of flexibility to understand new language. This is the most flexible and powerful approach, and a really common way to do it is by byte pair encoding, which I don't really have time to go into, but you can read about more on your own time or just ask GPT-4 about it. And byte pair encoding is used, for example, in BERT and GPT series architectures, which I'll be talking about momentarily. So in my code directory in my NLP with LLMs repo, in this GPT notebook, we are going to use the transformers library for the first time from Hugging Face. And we're going to use pipeline objects to very easily use a GPT model, and we're going to explore what tokens are. So you can open this up in Colab. The dependencies will take a moment to run. I imagine we want bigger, big enough. And we'll import this pipeline object for very easily using GPT. So while that's loading, I can explain the next bit of code a bit. Oh, I also want to clear all my outputs. So this pipeline object allows us to, in this case, generate text, because that's what we're specifying it to do. So we specify a model that we'd like to use, as well as a specific kind of task that we'd like it to perform. So in this notebook, we'll be doing text generation. But you could alternatively do sentiment analysis, named entity recognition, summarization, translation from a particular language to another. In this case, it's English to French, or feature extraction. I'm going to talk more about these kinds of tasks later on. But here you can see it running. So I'm downloading the model, and with GPT-2, which is the model that I'm very quickly downloading here, this model, because it didn't have that reinforcement learning with human feedback that I was talking about, it isn't a zero-shot learner. It doesn't do a very good job of figuring out what you'd like it to do without some examples. So it's what we call a few-shot learner, and that's at best. I'm going to get into this in more detail. GPT-3 was really a good few-shot learner. GPT-2 was really just capable of generating coherent text. However, I was able to coerce it here into doing some few-shot learning. So with my text example, I say the capital of Germany is Berlin, the capital of China is Beijing, the capital of France is, and then I gave it a constraint. I said, only use a maximum of 2 new tokens, when you generate your result. When I ran this in testing, it's really nice that here in front of all of you, it did Paris. But the first few times I ran it, I got Marseille, I got Lyon. So this model is not as good as the kind of GPT-4, the GPT-3 that you're used to, but it's still pretty cool. It's nice that it was able to get in that area, and that kind of gives you a sense of how these embeddings work. It was able to get very close in our abstract embedding space to the right point. It didn't quite nail it with Paris, but Marseille or Lyon is close. So more on tokens. You can load up this tokenizer for GPT-2, and you can explore what's in the vocabulary. So is love in the GPT-2 vocabulary? Yes, it is. Is Sinan, who created this notebook, is his name in there? No, it is not. So then when we encode a string like Sinan loves a beautiful day, what does it do? How does it handle this word that it hasn't seen before? So we can see here that it did encode it into, so these integer representations get used. So within GPT-2, this pre-trained GPT-2 model, there's specific integers that correspond to specific tokens, specific subword tokens. And we can actually use this convert IDs to tokens method to see what each of them are. So Sinan, this word that isn't in its vocabulary, gets broken into sin and an. And then also these words that have a space in front of them, there's actually a special character that denotes that space. And so space beautiful or not space beautiful would actually get a different token in this particular training. Cool. So that's tokens, and that's GPT-2. Gives you a little bit of a glimpse of Hugging Face and some of the other key content that we need. So going into more detail on the key kinds of language models that we have today, there are autoregressive models, and GPT is actually one of these. So what does it mean? With autoregressive models, we predict a future token. For example, with this sentence, the joke was funny, she couldn't stop blank. Autoregressive models predict what the final token should be at the end of a string, and that's it. And so autoregressive models are great for natural language generation. For example, GPT architectures like the GPT-2 architecture that we were just using. Autoencoding models predict a token based on past and future context. So they're not just at the end of a sentence. These can encode in the middle of a sentence. So he ate the entire blank of pizza. Predicting what that blank is what an autoencoding model is specialized to do. This makes autoencoding models more efficient at natural language understanding. So while natural language generation models also have to do encoding, they tend to be less efficient relative to a model that is designed to autoencode specifically. The BERT architectures are a great example of this kind of model. So what makes a language model a large language model? Language models with greater than 100 million parameters is kind of the cutoff that we can use for large. 100 million today actually isn't even that big because the largest models, English language models today, are models like Megatron, illustrated here, and these have 500 billion model parameters. And there are models that have been made in other languages. There's a Chinese model called Wudao 2.0 that has nearly 2 trillion parameters, and that's the largest model that I'm aware of today. Is size everything? No, it is not, and we're going to talk about that later in these slides. Interestingly, although uncommon today, technically speaking, so I want you to be aware of this, a large language model doesn't need to have a transformer in it. But the state-of-the-art LLMs today do have transformers in them, and typically they have many transformers in them. LLMs, regardless of whether they're a transformer architecture or not, they are pre-trained on vast corpora in order for them to work well. So very, very large data sets of natural language. How large? Again, more on that later. And generally, these LLMs are pre-trained, which means that they're able to, out of the box, perform well on a wide range of natural language tasks. And again, we'll get into lots of these different kinds of tasks later. We've already alluded to how some of them are able to do few-shot learning, which is what we saw with GPT-2 in the notebook just now, when it predicted Paris after it was given the examples of Beijing and Berlin. One-shot learning would be where you give it one example. So I gave it a couple of examples. If you just said, here's one example of translating English to French, translate this next thing from English to French, that would be a one-shot example. Zero-shot is the most powerful, and what we've become used to today with UIs like ChatGPT, where we don't need to provide examples, we can just ask for something and it does the task correctly, usually right out of the box. These LLMs can be fine-tuned to specific domains or tasks, so they don't need to remain general. You can fine-tune them to something specific, and that includes fine-tuning them to be aligned with what humans want. So one of the first big specific architectures in this space, one of the first big LLMs was ELMo from the Allen Institute and the University of Washington. ELMo stands for Embeddings from Language Models. It was an early transformer-based LLM, and it outperformed the previous state-of-the-art, which was recurrent neural networks, LSTMs, by a huge margin, and CNNs as well. So here you can see the gulf between the previous state-of-the-art and how ELMo performed in 2018. So this was the first time that people started to realize, wow, for a broad range of tasks, a transformer-only architecture could be a really interesting idea, a really powerful idea. BERT built on that, and it was created by the Google AI language team. The etymology of this is bidirectional, meaning that it's an auto-encoding language model, so it takes context from before and after. It's an encoder only, which is interesting. Earlier when we were talking about transformers, I showed how we encoded and then decoded. With BERT, we encode only. It learns representations. It creates language embeddings from transformers. So that's where BERT comes from. It excels at natural language understanding, auto-encoding tasks like classification, semantic search. So the way that this works is you're not trying to generate any language, because this is just an autoencoder. You're taking language and you're embedding it into an abstract space. And then from that abstract space, you can do lots of other downstream tasks, like classification or search. T5 came out a year later, and by Google, again, are you surprised? And so T5 stands for Text-to-Text Transfer Transformer. And so it is an encoder-decoder architecture, which is the text-to-text. It needs to be able to encode text as well as decode text. It uses transfer learning, so it's broadly trained for a wide range of specific tasks. We have a number of examples here, like translating English to German, assessing whether a sentence is acceptable or not, assessing semantic similarity between sentences, and summarizing. And I actually have a code demo coming up right now to allow us to try all of these different kinds of examples with T5 out of the box. And the key thing here that was the innovation was that the authors adapted a broad range of NLU tasks, like assessing whether a sentence makes grammatic sense, like evaluating the semantic meaning of a sentence, and converting that into a text-to-text format, into a generative format, which wasn't always the case before. This means that T5 is fast, it's generative, and it solves many NLP problems. So here is a code demo of T5. So we've got the T5 notebook here. Oh, the GPT for All inference notebook. I forgot that was running in the back. So how did it do here? Large language model refers to the machine learning models that have been trained on vast amounts of data in order to predict human written text with high accuracy and without bias. That's pretty good. It's pretty good for GPT-2. That's actually the best one I've seen. Sometimes it doesn't do a great job. And it's critical with even this, this is GPT-4 All, which I'll get into in more detail later on. It's supposed to be able to really be aligned with our intentions from RLHF and be like GPT 3.5 or even bold claim like GPT-4. But I still found that I got much better results if I said, please answer this question. If I just said, what is a large language model? It would often repeat other questions like, what is natural language processing? So on to T5. In this notebook, again, based on one by Sidney and Ozdemir, we'll use T5 out of the box for a broad range of NLP tasks. So I'm going to clear all outputs and run the first couple of cells while I explain them. So here we're going to be using the Hugging Face Transformers library again. We're going to be using the T5 model for text generation from the Transformers library. So Hugging Face Transformers comes preloaded with lots of the most common architectures for all of the most common tasks, making it very easy for you to take advantage of it. And so very often when we're using the Transformers library, we're going to create a tokenizer object as well as a corresponding model object. And as far as I'm aware, you always want those to be, I can't imagine, it seems like it would be mayhem to not choose the same model for both of these. And so the reason why I'm choosing T5 base here, as is common with large language models, you'll see for a particular name of model like T5, there will be several sizes of model available to you. So T5 base is the smallest one. So for the purposes of this demo running quickly, being able to download it quickly, that seemed like the best option. But there's like T5 XL, there's these other sizes that you could be using as well. And then once we have our tokenizer and our model loaded up, we can perform inference with it. So the first inference task that we're going to do is translation. So I'm going to go through these 4 different kinds of tasks that I had on the slide here. So we're going to encode a sentence with a specific request. So we're going to say, translate English to German, where is the chocolate? And we're going to return those tensors in a PyTorch format is all that this argument means. So in terms of the key arguments here that we're supplying, the input IDs is something that you obviously need to supply. We're going to ask our model to generate based on this encoded text that we've provided. Number of beams is a really interesting, powerful argument. So a beam gives you multiple different shots at getting the best answer. So when you've been thinking about these generative models probably so far, you would think about there just being kind of one thread that it's pursuing of like, let's try this word and then this next word. Beams gives you multiple kicks at the can where it says, okay, as I come along, you might get to the 3rd word or the 4th word and it might realize, hey, by this 3rd or 4th word, if I actually stick with this one path, I'm going to get much better results than if I just went with my first instincts when I was just generating the 1st word and the 2nd word. So it allows you to correct for suboptimal choices from early on in the generation. I'm going to set this running. No repeat n-gram size. This helps you get better results. So there's a problem that can happen in generative models where it ends up repeating things over and over and over. And so you can set a limit. You know, there's some words like the that you can't block, but some longer words. So here we're saying that any word that consists of 3 subwords or more, we're not going to allow that to be repeated in any of our responses. Maximum number of tokens is the maximum number of tokens that could be output here. And we're allowing early stopping so that we're not forcing it to have 20 tokens, which would be kind of silly in this circumstance. And it worked. So where's the chocolate? Wo ist die Schokolade? That is correct.
So the number of beans, is it always like the higher the better?
Oh yeah, great question from Ray. And exactly right. So with the number of beams, the more beams that you have, the better your results will be. But yes, the trade-off is that it requires more compute. It'll run more slowly. All right, so another example of this same architecture doing a different task. Without us having to change anything else about the way that we're doing it, I've taken the abstract from the T5 paper, and I've pre-processed it gently here to replace new lines. And then I just simply ask T5 to summarize it. That's the only prompt that I provide. I do have to change some of my arguments here. So for example, now I want to have a minimum length number of tokens. I want to force its summary to have at least 30 subword tokens in it. That's the only thing that I changed here. And I made the max length longer. So we have this window of 30 to 50. And transfer learning has emerged as a powerful technique in NLP. A unified framework converts all text-based language into a text-to-text format. Our study compares pre-training objectives. That's a pretty good summary of this abstract. Here's another one where we're doing something called COLA, which is it uses the corpus of linguistic acceptability to check for grammatical correctness. Wow, that was fast. I didn't expect it to go quite that quickly. So you can say, so COLA is this, remember T5 was created to do a broad range of NLP tasks. So we can say COLA sentence, and it will know what that means. It's using COLA as a verb. And so this class is going poorly. Is that grammatically correct? Yes, that is acceptable. And then if I COLA the poorly is going class, is that grammatically acceptable? No, it is not. Question up at the front.
So we just have to know all those, for example, COLA sentence or instruction in advance. Do you have so many or just few of them that we have to know? This task we have to start COLA sentence at that.
So the question is whether, so there are specific tasks, specific abstract tasks like COLA sentence that you would just have to know that the T5 algorithm was trained on that. But like other large language models, it is a few-shot learner. It might be a one-shot learner. You might even be able to get it to do some zero-shot learning in some circumstances. So you can challenge it with kinds of tasks that aren't necessarily in its training data set as well.
So is this sentence grammatically correct?
Yeah, absolutely. So the question is, would it work to just say, is this sentence grammatically correct? Let's try it. So it might not answer in that like standardized output of like unacceptable. No. Interesting. Yeah, so great question there. And so last one here is a semantic text similarity benchmark, STSB. So we provide two sentences, how to fish and guide for anglers. So are those two sentences semantically related? Is the meaning similar? And this STSB, semantic text similarity benchmark, provides a score on a scale of 5. So we don't need very many tokens here, so I just set a max length of 3, and it prints out 3.2 for this sentence. You know, both these things are about fishing, so that makes sense, how to fish. If we have this second sentence where it's how to fish and a guide for hikers, semantic similarity comes out as 0. The question is whether there's a way to get a confidence score, and the short answer is, I don't know, but you can try. So GPT, this is an algorithm that a lot of people, a family of architectures that we're really excited about today. And so what's the etymology of GPT? It's generative, which means autoregressive. So it's putting text on the end of sentences. It's pre-trained, which means that it's designed to perform very well at many kinds of tasks, 0, 1, or few-shot learning, depending on the era of the model. And the T is transformer. Spoiler. So a bit about the OpenAI GPT family. We've had 5 major versions released now. GPT first came out in 2018. It was very small and accepted only 1,000 tokens as an input. GPT-2 was the first one that made a lot of public noise. And this one had 1.5 billion parameters, which is relatively small today. But as we saw, it was capable of generating coherent text. We've already been using GPT in today's training. GPT-3, huge model in comparison, and a lot of emergent properties that people weren't expecting. GPT 3.5 and GPT-4, the big change here was that RLHF, that reinforcement learning from human feedback that I talked about earlier, that aligns it with what humans are looking for, and it ends up having amazing responses, way better than we'd expect. We don't know how big GPT-4 is, but it's probably bigger. We don't know for sure. They might have used tricks actually to make it smaller, more efficient. And a really big thing about GPT-4, it's hard to get access to this API yet today, but there is a version of the API that allows for 32,000 tokens as an input, which is huge. GPT-4 also has vision. So 3 major ways for you to be thinking about how you can be using LLMs. The first way is prompting. So a ChatGPT style UI allows you to do that. You can use the OpenAI API, and we will be using GPT-4 in the OpenAI API in today's class. Or, like we did with the GPT-4 all that we downloaded, or the T5 model that we downloaded, or the GPT-2 model that we downloaded, you can use it at the command line with your own instance that you have on your own machine. The other major way that you can be using LLM is for encoding. So we already talked about this earlier. So converting natural language strings into a vector. You can read a blog post about this here. Using these encodings for semantic search. So converting all of your documents, using BERT to convert those into encodings, and then using a cosine similarity score to compare proximity between those documents and searching by meaning over your documents. The third major way to use LLMs is transfer learning, wherein we fine-tune a pre-trained model to a specialized domain or task. And so this, for example, could mean you could take BERT out of the box, but you have some financial application, and so you fine-tune BERT to be able to classify financial documents specifically, or to be able to search over financial documents specifically. Or you could be using T5, you could be fine-tuning T5 to generate strings that correspond to integers. This sounds like a pretty random task, and it is, but we're going to be doing a bunch of it in today's class because it was a nice, small task for us to be able to do, and thanks to Sean Kosla for thinking of doing it. All right, so this is the end of our first section. In it, we learned that attention with transformers is all you need for natural language processing. We talked about how autoencoder LLMs are efficient for encoding, that is, understanding natural language. Autoregressive LLMs can encode and generate natural language, but typically they're slower than autoencoders. We can fine-tune LLM results in specialized models, which is a really cool thing because it means we can be developing our own proprietary LLMs for our own use cases. And RLHF in particular is a fine-tuning approach that aligns our outputs with human desires. So we've gone over an introduction to LLMs. Now let's talk about the breadth of LLM capabilities. So without fine-tuning, pre-trained transform-based large language models can, for example, they can classify text. This means that they can take natural language and do sentiment analysis on it, say that it's positive or negative. Or you can have your own specific categories. So you can list for GPT-4, it's so powerful, you can say, I have these 4 specific categories that I'd like you to be able to classify into. Here's an example text. Which of those 4 does it belong to? And you could do that for a whole bunch of pieces of text to label your data for you automatically, which is a really powerful thing that you should be thinking about doing with LLMs so that you can have your own smaller, powerful machine learning models. You can recognize named entities, so you can have it extract people, locations, or dates, which could be useful for some application that you have. You can tag parts of speech like nouns, verbs, and adjectives. You can provide it with context, you can provide it with language, and ask it to answer questions about that. So it means that you don't have to search for the answer across some large piece of context. You can ask it to summarize things. So we already saw T5 do this. It'll create a short summary, but preserve key concepts. You can ask it to paraphrase, which is kind of like summarization, but it means keeping the length and rewriting it in a different way while retaining meaning. You can ask it to complete things like predict next words. You can ask it to translate. And this includes, if we had it in the training data, you can translate from human language into code, or from code into human language, or from code to code. If you learned R, that was your bread and butter for a long time, and you're now learning Python, you can just ask it to convert your R code into Python for you and explain what it was doing. You can have it generate. This is kind of like completing, but completing, my idea here with completing is that you're taking like potentially a big explanation and just saying, what do you think the next few words should be? With generating, we're potentially asking it to generate paragraphs or much more. And it could also be code. We could be asking an LLM to generate large chunks of working code for us. A great example that came up a few times yesterday in my intro to deep learning class was people were asking, how do I choose good starting hyperparameters for a particular problem? How many layers do I want in my deep learning model? How many neurons do I want in each layer? Up until March, when GPT-4 came out, I would have said to you, well, find relevant literature on this problem and see what they're doing and use that as a starting point. Now, I'd say ask GPT-4 to just create it. So say to GPT-4, I want to solve this problem. What's a good starting architecture? Create the code for me in PyTorch. Saves a lot of time. And another LLM capability is chat, so engaging in extended conversation. I came up with all of these on my own, but on this next slide, all of these were provided by GPT-4. So I gave it those first 10. I was like, look at all these things that I thought of that LLMs could do. Did I miss any? And it can effectively provide an infinite number of things that it could do, right? So text simplification, abstractive summarization, where it's not just summarizing, but it's actually condensing and rephrasing and synthesizing at the same time. Finding errors and correcting them. Finding sarcasm, which is a crazy thing that we thought would be hard to do. Finding intent, that's also a really cool thing for your kinds of applications. So you could be, finding intent is a really good one for a lot of applications. So if you build an app and you want your users to be able to ask you anything, you can ask the model to convert their question into some intent. What does this user want? And then you could take that intent and have it potentially go into a set number of specific pathways within your platform. You could even, going back to the point that I made earlier about the classification thing, you could actually say, there are 5 options that we could go for in my platform at this point. There are 5 pathways. And you could describe what those 5 are. Which of the 5 is my user asking for? So your user doesn't have to select from a drop-down box. They can just type a natural language query, and then you figure out their intent and figure their path through your platform. Sentiment shift analysis. This is an interesting one where the sentiment in some natural language changes. So you can imagine over the course of like a customer service conversation, the person phones at first and they're in a friendly mood, and then there's a shift. So detecting that. Content moderation, keyword extraction, extracting structured data, so taking from natural language or tables or lists, taking information out and putting it into specific fields for a structured database, providing recommendations like books, films, music, travel. Although you could use GPT-4 to music travel. You can take me to 18th century France. Who should I listen to? Creative writing like poetry and prose. Stylometry. This was a word that I didn't know before, but GPT-4 taught me, which is like analyzing anonymous text and identifying the author. So you could provide text and say, who seems to have written this? And it'll say, it's definitely a Shakespeare. It'll try to do that. And text-based games, this is fun. Even with ChatGPT at Christmas, I was at a Christmas party. My sister hosted a Christmas party. And a bunch of people at the party hadn't used ChatGPT yet. It was sacrilegious. And so it turned out that a lot of people there liked Harry Potter a lot. So my friend and I, who had a lot of experience with ChatGPT, we used it to create a Harry Potter quiz game. So we split the people at the party, all these Harry Potter fans, into 2 groups. I don't know anything about Harry Potter, but I was able to do a Harry Potter quiz by having it suggest questions. Because we were using ChatGPT, which was powered by GPT 3.5 in December, there were some hallucinations. If I was to do it with GPT-4, there would not be hallucinations, very unlikely. And then another thing that's happening more and more, and I'm going to talk about this more later, is multimodal models. So being able to generate speech, generate music, generate images, generate video, or be able to understand those modalities. We're seeing more and more of that. And we're going to see models that have more and more of that all at once. So how can you interact with LLMs and make use of all this functionality? There are click and point chat interfaces, for example, ChatGPT, which probably most of us have used. You can also, in Hugging Face repos, there are often places where you can interact with the models there. So here is a relatively new model created by the same people that made Stable Diffusion, the image generation algorithm. And so this is Stable LM, Stable Language Model, and it's tuned, which in this case means it's tuned on human instruction response pairs. So it's designed to be able to probably do zero-shot learning on a lot of different tasks. It's designed to be aligned with us. And 7 billion parameters are in the model. So we can ask it something. Gosh, there's always all this pressure. I should have come prepared with something. Come on, give me something. There's got to be something.
I have a question. Can you download these models and run it locally?
Can you download Hugging Face models and run them locally? Great question. Thank you so much. And yes, you can. We're going to have lots of code demos in today's class where we do exactly that. But that was a really great question. And that was fast, wasn't it? For something that you can use for free that's just being hosted. And the OpenAI GPT Playground. This is cool. Who else has used this here already? Yeah, some people, a small percentage. So what this allows you to do, this allows you to use the kinds of query parameters that you'd be able to adjust at a command line interface with arguments inside a click and point user interface. So Text DaVinci 3, this is a GPT-3 model. And so temperature, for example, this controls randomness. So what was that question again? Can you download Hugging Face models and use them yourself? If you turn the temperature down, it will be more deterministic. If you turn the temperature up, it'll do wackier things. And so I guess things like 0.7 is like a decent kind of middle ground between deterministic and wacky. You can change maximum length. There's lots of other parameters that you can read about. Ooh, show probabilities. Oh, that's cool. So that actually shows you, yeah, let's do that so you can see that for each of the tokens. So what this provides is it provides you with percentages of how likely it was to pick the particular words that it did and the words that it considered as alternatives. So pretty cool. So this gives you another way to interact with these models. I can really quickly show you, if you haven't used it before, I mean, you've got to do this. It's insane to me if you don't spend $20 a month to get GPT-4 within ChatGPT Plus. Like, you don't need to be on a waiting list. It's $20, and it is so incredibly good. You know, the explanations, like, you know, I was working on this last night, and so I was asking, and actually this ended up being wrong because of the cutoff that it has here. But it acknowledges that. It says, because of my knowledge cutoff. But explaining LIME in machine learning, very specific questions about arguments on commands. It just goes on and on and on. I mean, and very detailed, like code, like working through code and helping me with it. So me providing it with an enormous, look at this huge block of code that I provided it. Huge block of code, and this is nothing for its context window. It can handle thousands of tokens. But I provide all of that, and I say, I want to be able to calculate loss on the validation data. And it writes in the code that I need to be able to do that. So it adds in this new method and leaves everything else intact. It's amazing. That would have taken me half an hour to figure out on my own, and it was a minute. It's wild. So if there's nothing that you take away from this class, it's use GPT-4. So we've seen staggering progress in the GPT family. So GPT-2 was capable of coherent generation of long-form text. We talked about that. GPT-3 was able to learn new tasks via few-shot prompts. InstructGPT, which came out a year ago, was able to fine-tune GPT-3 with reinforcement learning from human feedback to create GPT 3.5. This enables learning of new tasks via zero-shot prompts, and it aligns outputs so that you'll see these capital H's. Sometimes you'll see two H's. 3 is nice. H, helpful, honest, and harmless. So we're trying to make these systems so that they can't be misused. And then ChatGPT came out in November. This intuitive interface added additional guardrails around GPT 3.5 as it was being released into the public. And then GPT-4 came out just 2 months ago, and it's markedly superior to any of the preceding LLMs. It has reasoning and consistency over long stretches. So this means that on the uniform bar exam, which is a text-only legal exam, you spend years and years studying to be a lawyer. And up until March, you could say, machines can't do my job. Machines couldn't do the bar exam. And they couldn't. The GPT 3.5 scored at the 10th percentile on the uniform bar exam in the US. GPT-4 is at the 90th percentile. So it went from 9 in 10 bar exam sitters, being better than it to 9 in 10 being worse than it in a year. The alignment to me is wild. So sometimes I won't tell it that it did something wrong. It will give me an output that wasn't exactly what I was looking for, and I'll just ask my next question, which required, say, some clarification on the previous. And it knows. It blows my mind, this alignment of it knowing that it was slightly off with what I wanted. And so it apologizes. It says, I'm sorry, you're right. Here's more what you were looking for. And it was very subtle. The context is huge. So this isn't publicly available yet, but there is a waitlist for this. You can get access to the GPT-4 API that has a context window of 32,000 tokens. That's about 25,000 words. And that corresponds to, I asked GPT-4 to do this math for me, about 100 single-spaced pages. That's wild. And the accuracy is 40% more factual, it says. So I don't know how they calculated that number. That's in their technical report. Because my experience of using these tools went from I see mistakes periodically to I don't see mistakes. Yeah, so 40% more accurate, 80% less disallowed content relative to 3.5. The code generation, as I already showed you an example of, is absolutely mind-blowing and you need to be using it. So image inputs are also, this isn't publicly available yet, but it allows for image inputs. So you can take a photo of your fridge, this is one of the examples that they gave, and say, what can I make for dinner? The style has become so good. GPT-0, which was this tool that was designed to prevent kids from plagiarizing on exams, doesn't work anymore. With GPT-4, they can, it frequently says for me, 0% chance that this is AI generated. Maybe that'll catch up, I don't know. But it'll get better and better, because you can have it, the trick is to provide it with examples of your style. So you give it with well-written stuff that you've written and say, generate more in my style. And then it's got great plugins. So it's got a web browser plugin. So I think this might tie to a question that we had up here at the front. So you can search over the web using GPT-4 style queries. The plugins aren't yet publicly available, but there's a waiting list. There's a code interpreter, so you can actually be having it understand and execute code, which is wild. So these two plugins are actually created by OpenAI. And then there's lots of third-party plugins that are becoming available, like Wolfram Alpha for mathematics, Kayak for searching for a car in a hotel for your next trip. So we've got a hands-on code demo of the GPT-4 API, and then I'll let you have a break. So this is a quick one. GPT-4 API. We've got a Colab notebook. And in here, so let me clear all outputs, just like we have in all the other ones. In order to use this, there's two things that you would need. You need to already have been approved for the GPT-4 API. A link to the waitlist is here. And then once you have been approved, you need to go and create your API key. So in the OpenAI API, I have these various keys. So this Colab demo one I created for this purpose. So you create these GPT-4 API keys. Well, or for any of them. If you don't have access to the waitlist, you could do this same demo as me. You can use GPT 3.5 or one of the earlier architectures. And you use the API key for that as well. So dependencies are simple. We just need this requests library for making API requests, JSON for handling JSON structure, and paste the key, And here we go. Then we can, so if you didn't use this kind of get password thing, you can just hard code your API key with this line of code instead of this line of code, right? So if you're doing this at home, you don't need this secret key rigmarole. And then the code is pretty simple. So we've got this generate chat completion code. So here's where you specify the model that you want to be using. And so if you don't have GPT-4 access yet, you can just use GPT 3.5 Turbo. It's the next best. Temperature controls randomness. I think this is actually a range of 0 to 1. In some other models, it is 0 to 5. And then we're saying that we're not going to require it to have a cap on the number of tokens. Content type JSON, you provide the API key, of course, and then you provide the specific arguments, and you provide the code. So this response code 200 means okay. So if the response goes well, so if this API call goes well, then we will return the result. Otherwise, we return an error code. There is a cool thing about using the API that you don't get in the UI, which is that in addition to providing user content, so write a sentence about John Crone, where every word begins with the next letter of the alphabet, starting with the letter A. In addition to that, you can also specify context, system context. So this is optional, and the default is to say you are a helpful assistant. I don't know, I actually haven't spent any time thinking about what other things you might want to write in there. You are an unhelpful assistant, but you can provide the system with context that will provide a different result. And yeah, so there you go. Although being considered diligently, every fine gentleman John Crone learns medical neuroscience. I do have a neuroscience PhD, opening powerful, qualified research studies to understand various wonderful, xenomorphic, young, zealous brains. I ruined it on the very last word. That's too bad. Almost got it. Oh, H and I are missing? Oh, there we go. Well, but still did pretty well. I saved a really good one that it did of me that had actually a lot of context about my real life in it. It blew my mind, and I've saved that one. I might just use it as my bio at conferences from now on. So yeah, so that's how you can use the OpenAI APIs. I hope that you enjoyed learning that. And I hope you've enjoyed all of this training so far. So we're now through the second of 4 sections. We've learned that LLMs are capable of a staggeringly broad range of tasks, that thanks to reinforcement learning from human feedback, more data, and guardrails, GPT-4 is zero-shot and mind-blowing. The cutting edge in LLMs is advancing rapidly. The playgrounds and APIs are extremely easy to use. Okay, so I've introduced large language models. We've gone over the breadth of LLM capabilities. Now in section 3, the part you've been most excited for, we're going to talk about training and deploying large language models. So in this section, we're going to talk about hardware options. We're going to talk about the Hugging Face Transformers library in more detail than we have before. We're going to go over the best practices for efficient model training. We're going to talk about open source LLM options so that you can have your own LLM on your own proprietary infrastructure. We're going to talk about the PyTorch Lightning library that makes it fast and easy to deploy and train LLMs, including hands-on examples of single GPU fine-tuning to a specific task and multi-GPU fine-tuning. We will wrap up with deployment considerations. So for hardware options, if all you have available to you is a CPU, this is okay for inference if you're using a smallish large language model and if that model is quantized. So at the very beginning, our very first hands-on code demo was using that GPT-4all command line interface. So we downloaded GPT-4all onto our own server. Happened to be a cloud server, but you could have done it to your own server. And that was a relatively small LLM. We could fit it onto a single server. And not only that, but it's quantized, which means that this is something that you can do before inference time, where you reduce the complexity of your model weights substantially. So the default precision is 32-bit single precision for model weights, but you could have it go down to potentially as low as about 4 bits is what we see as about kind of the low threshold. And so that means that your model is much, 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 much smaller. And it means that you can run efficiently on a CPU. And so that could reduce your costs because having CPUs running your LLM would be cheaper than having GPUs doing it. This is not practical. You cannot train an LLM of any size on a CPU. So inference, yes, in specific circumstances. Training, no. GPU, this is your typical choice for training and inference. You likely need multiple for training. So with a lot of LLMs, these are going to be too big to fit on a single GPU. And depending on the size of the architecture that you go with, if you wanted to run GPT-3 or something of that size, 175 billion parameters, you're going to need like a dozen GPUs just for inference time. And there are also specialized AI accelerators out there in addition to GPUs. So these include things like TPUs you may have heard of. These are available to you in Google Colab for free. These are tensor processing units. GraphCore has something called an IPU, which is distinct from CPUs and GPUs. So you could have an IPU in addition to CPUs and GPUs that you already have on the machine. And these are designed for massively parallel mixed precision operations. We're going to talk about mixed precision more later, but essentially this allows you to speed up training. And Amazon Web Services, I was actually alerted to this because if you listen to current episodes of my podcast, Super Data Science, there are ads for these things, the Trainium and Inferentia accelerators, but I hadn't heard of them until Amazon approached me to create these ads, but these sound really cool and you can get AWS boxes that have these specialized chips for training and for inference, designed explicitly for that, and they handle LLMs really well. So there you go, a useful commercial interruption. So the Hugging Face Transformers library, we've already been using this a number of times in notebooks in today's class. You've seen how easy it is with transformers to pick the model of your choice and use it for the task of your choice. There are thousands of pre-trained LLMs ready to go in the Hugging Face Transformers library. And it supports all of the most popular model architectures, including all the ones that we've talked about in today's class, like BERT, the GPT-Family, T5, and so on. Hugging Face supports multiple languages. So some models that it supports have over 100 natural languages. It's task ready. So as we already saw in the GPT notebook that we were in earlier, a wide array of different tasks is supported with transformers. So in the GPT notebook, we used the pipelines functionality to get access to those tasks. And then with other kinds of models like the T5 that we used, you had all these different kinds of tasks supported inherently by the model. The pipeline object is super easy to use for inference. We already went over that. I'm not going to go over it again, but because there's too many other things to cover, but super useful tool for very easily doing inference. Hugging Face Transformers offers interoperability, which means that with ONNX, the Open Neural Network standard format, we can switch between PyTorch and TensorFlow. So whichever of those automatic differentiation libraries you are most familiar with, you can use with transformers. And so this means that actually you could mix and match seamlessly. So PyTorch is more Pythonic, so it's often more fun to use. So you might want to create your model architecture in PyTorch and train in PyTorch, but then when it comes to deployment, you want to take advantage of some specialized TensorFlow library for serving up the model. They have lots of adjacent libraries for serving in people's browsers, on small devices like phones and cars that have relatively small computers, edge devices. So there might be these TensorFlow libraries that you want to take advantage of. And so with transformers, no problem, you can do that. In terms of efficiency, it provides built-in quantization, the thing I was talking about earlier for compressing our models really small. It has built-in pruning and distillation. These are other kinds of approaches for shrinking your model size, and I will talk about those more near the end of this training. It's got a great community, so it's got a model hub for sharing and collaborating. We're actually going to take advantage of that. We're going to train, it would take too long in class time, but I'll show you exactly a model that we trained for the purposes of this class, and I'll show you through all the steps of doing it. I'll then show you how we can upload our model to Hugging Face and use it there in the Hugging Face UI, or download it and use it ourselves on our local machine. It's research-oriented, so the latest models from research papers are available there, and there's extensive tutorials and detailed documentation. So an amazing library, a great ecosystem, and it was a delight to learn so much about it for today's training. So let's jump into another hands-on code demo that will show some new functionality that we haven't explored yet in the Transformers library. So this is the GPyT, not GPT, but GPyT code completion notebook. So in here, in the interest of time, I'm just going to show you what's in this notebook. Actually, you know what? It's pretty fast. So in this notebook, clear all outputs, load our dependencies. So my only dependency, other than the ones that are already available, the only additional one that I need to install here in Colab is the Transformers library. And then we're just going to use PyTorch as well, import that. So a cool thing that I hadn't shown you yet here is that we can be using any models that have been uploaded by anybody to Hugging Face. So this is a specific one here. This isn't like one of those core models. Like previously we were using T5 base, and we didn't have to specify a specific Hugging Face repo. We just specified T5 base. But we can take advantage of, so this one, you could have come across it in a Google search, or someone could have recommended it to you, but there's this GPyT model, which is a GPT architecture, but is trained from scratch, not fine-tuned, on Python code from GitHub. So it won't be able to do natural language tasks. It will only be able to do code generation tasks. But that's cool. That's exactly what we decided that we wanted to do here. So it's a very small model. You can see here it just took it took 27 seconds for me to download the tokenizer as well as the causal language model. Causal here means autoregressive. So like GPT architectures, it's predicting next words. It's not encoding. Well, it is encoding, but it's not just an autoencoder. And then so here we go. Here's an example of code that we're going to have it run on. So this is running on this specific instance of Colab that I have running here. And so we pass in these imports as suggested text, and then we ask it to continue. And so we provided various constraints. We've said that we want the max length to be no bigger than 8 tokens beyond the original text that I provided. And this argument here, I just did it to suppress a warning. If you don't do that, it'll just tell you that this is what it is doing automatically. And yeah, so we use our tokenizer to encode our query, and then we run it through our GPyT model that we've downloaded, and then we ask it to decode, and we just reformat it so that we get the new line characters printing out nicely. And there you go. Yes?
You may cover this later, but how do you address some of the security and privacy considerations when downloading a model like that?
Yeah, so the question is, how do you address the security and privacy concerns when downloading a model like that? I'm actually surprised that that's where your security and privacy concerns are coming up, because now all of a sudden, any information that I provide to it is just, it's local to me. So the question that a number of people asked me over the break, which is one that is worth addressing for the whole class, is the security and privacy concerns should be if I'm sending it over an API to, say, OpenAI. When I'm downloading it locally, what's the security and privacy concern? All right, so there are lots of other examples of third-party models. Obviously, there's thousands of them out there. And Sinan, in his notebook here, he has lots of other examples. So a Turkish GPT-2. He's got GPT Neo, which is cool. It's a very small model, so just 1.3 billion parameters, but it can do a lot of simple tasks reasonably well, as he shows here in this notebook. So pretty cool thing for you to explore there if you want to explore more third-party models. Okay, back to the slides. All right, so now that you know how to download your own models, you might want to train them for some specific task of your own. And so how can you be doing your training most efficiently? I'm going to go over the key ways that we can do that. So we've got gradient accumulation, gradient checkpointing, mixed precision training, dynamic padding, uniform length batching, and parameter efficient fine tuning with low rank adaptation. We're going to cover all of those right now. So let's get started with the IMDb GPU demo notebook. So in this notebook, we have, I'm going to clear my outputs here. So this is based on code that Sean Kosla from my team at Nebula created. And so we're going to use the Hugging Face Transformers library to illustrate how we can fine-tune an LLM to a specific task. In this case, the task is going to be predicting the sentiment of a film using a database from the Internet Movie Database, IMDb. So some of the movie reviews are positive, some of them are negative, and so we're going to fine-tune an architecture to excel at being able to do that. Although in practice, in the constraints of time, we're not actually going to take the time to train it long enough for it to work really well. But you can run it for longer on your own. So if you are running this for the first time, you'll want to go to runtime and go to change runtime type and change from the default no accelerator, which is CPU only, to a GPU. And so we're going to use PyTorch as our automatic differentiation library. We're going to use Hugging Face transformers, obviously. There are some NVIDIA imports here that are specific for tracking GPU usage, because we're going to use that to illustrate some of these efficiencies that I was talking about in the slides, these various things. Those will show up in here. We'll use this management library to print out GPU usage and see how that's working in our favor. And then we also, just for a bit of fun at the end, sometimes people worry about being able to do explainability. And so we've got a little bit at the bottom using Lime to explain how this big LLM is kind of producing some of its results. So these are just utilities for GPU benchmarking. I'm not going to go into them in detail. We'll see them print out. This line of code here is letting me know whether my GPU is available. So if you're, as opposed to using Google Colab, if you set about having the NVIDIA drivers working properly on your own server, it is a nightmare. It's nice in Colab to just have this work really easily. And so we can see that our CUDA device, our GPU, is available. CUDA being programming language that's used on NVIDIA GPUs. And so this here is just a bit of a query to say, if we're using it, if the CUDA device is available, if the GPU is available, let's use it. If it's not available, then let's use a CPU. So we're using GPU, which is great. And then here's that GPU utilization method that we just created up here. And so it's telling us what GPU we're using, device 0, because you can have multiple. So it's 0 indexed. The first GPU is device 0. And it's telling us how much memory is occupied on the device. And as I was preparing for this class, it kind of frustrated me that this showed 261 megabytes. So I asked GPT-4 why that happens. Why isn't it 0 megabytes? And it's because just the initialization of having the CUDA library and various dependencies on there, it takes up about this amount of space.
How much RAM is needed to run this?
Oh, very little RAM is needed for this. So you can see here, just as like a quick example of how we can send things to the device. So here we're just creating a really simple tensor of ones, and we're sending that to a device, and then we're seeing how that changes utilization rates. So it's just as a quick example. And so it's this to device that allows us to be taking advantage of the GPU. So you've got to include that in your code, in PyTorch code, for example, when you want to be transferring weights over there. So the model that we're going to use, that we're going to start with, it's created by Microsoft. So our pre-trained model is going to be this dialogue ranking pre-trained transformers up-down model. So it's a GPT-2 style architecture. So it's generative, and it was trained for a task related somewhat to movie review sentiment classification. So it was specifically designed for predicting how many upvotes a comment made online will get. So it's kind of good at interpreting human comments and deciding sentiment in a way on them. So it seemed like a reasonable starting point as a model to get going with. And so let's load in our tokenizer. We're saying that we'll allow it to have inputs of up to 1,000 tokens. Here we are setting the number of possible labels that can come out. In theory, we could actually just have one, I realized when I was looking at this the other day, but I didn't want to keep futzing with it at this late stage in the game. But technically, if you only have 2 labels, you only need 1 outcome. And ignore mismatched sizes. So this allows us to have 2 output neurons on a model that was pre-trained with just 1. And that's also related to why we get this warning that says you should probably train this model on a downstream task to be able to use it for predictions, which is exactly what we're going to do. So this is related to us Frankensteining it, right? We're taking it originally had 1 output, now we're forcing it to have 2, and so out of the box, it's not going to be a very good model. But if we fine-tune it on a downstream task, it will be useful. So let's look at our GPU utilization. So we're now using 2,500 megs on our Tesla T4 GPU, and that's a small fraction. It's about a sixth of the GPU space that's available on that kind of device. So loading and preprocessing the data, I don't really want to spend too much time going through the specifics of how we're just like loading the data and working through it, because you're probably not going to go home and work on this movie sentiment problem. I want to just be focusing mostly on the library. But so we'll just kind of talk about it at a high level. We're using this load dataset function, which is provided by the Hugging Face. So in addition to the Hugging Face transformers library, we're also using the Hugging Face datasets library, which is an easy interface for accessing lots of different databases, including the Internet Movie Database here. So, and then we specify, so we're just taking 25 movie reviews for our training set and 25 for our test set. This is a toy size. You wouldn't train a serious sentiment classifier with that small amount. The full data set, if I remember correctly, is 25,000 and 25,000. So a total of 50,000 movie reviews. And so here you get an example of, so here's our 3rd movie review in the training data set, and you can read it. It's in natural language. If only to avoid making this type of film in the future. This film is interesting as an experiment, but tells no cogent story. It's clear to me as a human that this is a negative review. And the label corresponds to that. So 0 is negative, 1 is positive review. Now, this model won't actually be able to train because for demo purposes, these 25 and 25 that we selected, all of the labels are negative. So you can't train the model with only 1 label. If you want to do this on your own later, increase this to, you could do the full 25,000 and let it train for longer, but I just wanted this to run quickly. So this doesn't really matter because actually what I'm showcasing in this notebook is efficiency best practices. So memory management, compute management, and we can do that without actually being able to train effectively. So here is the this movie review converted into tokens, right? So we're using the same tokenizer or a tokenizer corresponding to this same Microsoft comment up-down model. Out of the box, these are the tokens, the subword tokens that it assigns. And here is some code for preparing our data for being passed into the model. So our model is expecting input IDs is the standard Hugging Face terminology for our model inputs. IDs meaning subword token IDs. So input IDs, you'll see that everywhere when you're using Hugging Face models. And so we're taking our movie review, so a given review, the text from it, tokenizing it with our tokenizer, converting that into an input ID. We are truncating, which means that if the movie review is longer than 1,000 subword tokens, we truncate it, we cut it off at 1,024. That was a hyperparameter that we set at the top, the 1,024. And then if a movie review is shorter than 1,024, we pad it with a special padding token so that it gets up to 1,024. So this means that all of our reviews in our training set, as well as in our test set, will have the same token length. And yeah, here you can just see what the structure of these data sets are. So these data sets that we're going to pass in, they have 2 columns. These are arrow structures, which are very efficient data structures for, they're pandas-like, but they're extensible to multiple machines. And so I've asked for the column names on this arrow object, and it tells me that I have a label, which is obviously whether the movie is positive or negative, and our input IDs. So it's a bit of a straw man. So having all of those extra padding characters is computationally inefficient, but we're going to use that inefficiency in this vanilla training model. It's relatively naive. And so we've got some arguments specified in a dictionary here. So we're saying where our output directory is, we're just calling it temp. You can choose an evaluation strategy. So I'm setting it to no because I know all of my samples have the same label. They're all zeros. So what's the point in also evaluating? You're not going to see anything interesting. But if you want to change this, the other options are epoch, which means that you'll test on your validation data after every epoch of training, or you could alternatively set it to run after a set number of steps, in which case you'd set this to the string steps and then add another argument. I can't remember the name of it, but there's another argument you can include that says how many, every 10 steps or every 100 steps I want to do validation. I want to evaluate on my held out data. And per device training batch size. So we're doing a batch size of 1, and we are training for 1 epoch. So just to get some results really quickly here. We pass all of these default arguments in as a training arguments object into our trainer from Hugging Face. So this is a really convenient method that allows us to specify our model, which we pass in, specify what our training data set is, what our evaluation data set is, what tokenizer we're using, and our additional arguments. So really straightforward. So easy to use. And once we have our trainer instantiated, we can use the train method on it to actually do the training. And so it was running here as I was explaining what's going on in this cell. We got a result, and then you can print the result. So it says that it had 25 training examples. It ran for 1 epoch. Here's the batch size. And it's providing us with some summary stats down here, like our GPU memory occupied. So this is the whole GPU. And it's also telling us how quickly it ran. So the samples per second was 1 and change samples per second. So overall, it took 24 seconds. So this is our baseline in terms of compute time as well as memory usage for this particular task. Now let's learn about ways that we can be doing this more efficiently. So first way that we can be doing things more efficiently is gradient accumulation. With gradient accumulation, we maximize our GPU usage. So we split a synonym for batches is mini batches. And so let's say we had a sample size of 8 in our batch, in our mini batch. With gradient accumulation, we split that mini batch into some number of micro batches. And so if we set our number of micro batches to 4 in this case, then we'll end up with 4 micro batches of 2 samples each. And we do a forward pass on each micro batch separately on our GPU. So we're maximizing the use of our GPU. We save our gradients from each of those micro batches separately, and then we perform backprop on the accumulated gradients once we have all of our microbatch gradients. And so this allows us to have larger mini batches, which means fewer training steps overall. It means fewer rounds of backpropagation on our gradients and faster training. But you don't have to take my word for it, because we can do it. So here in this cell now, we're using the same model, but we are setting a new default argument. So remember, we had this dictionary of default arguments. We're adding in one additional item into that dictionary, which is the gradient accumulation steps. So now we're breaking up our batches, and we end up with a faster training time. So this approach ends up using even more GPU memory. So we went from 12,000 to 13,000, but the trade-off is that we were able to increase how many samples we were processing per second. So we went from 1.03 samples per second to 1.3, which means that our overall training time went down from 24 seconds to 18 seconds. Our next trick is gradient checkpointing. So in a typical forward pass, we store all of our intermediate outputs for backprop. So each layer of our neural network has activations, and typically we're saving all of those for backpropagation. This is compute efficient, but it's memory inefficient because we have to save all of those. With gradient checkpointing, we save a subset of all of our outputs. So we don't save all of our intermediates, we only save a subset of them, and we recompute others as needed during backprop. So what does this mean? This means that we're going to have more memory efficiency, but it's also going to increase our compute because now we're not going to have all of those intermediate values stored conveniently. So let's see how that trade-off affects us. In this cell here, this gradient checkpointing cell, so I add in another additional argument. It's a binary argument, gradient checkpointing. I set it to true. All the other code is the same. And now our training is taking longer. But the trade-off is that we are going to have less memory usage. So come on, there it is. So our training is now slower than it was. So we went from 1.3 samples per second to less than 1. So our training time bumped up from 18 seconds to 26. But our memory usage halved. We went from 13,000 megabytes of memory down to 7,500. Automatic mixed precision. So typically, as I mentioned earlier, we use 32-bit floats, single precision, to store our model parameters, our activations, our gradients. And so these are all of the bits, the 32 bits in a single precision float data point. A half precision float has just 16 bits. And so it's half the size. It requires half the compute to process. This preserves memory and speeds training. Automatic mixed precision means that it automatically figures out what kinds of circumstances we can be dropping to the half precision and what circumstances we should be sticking with the full precision because we'll need it. So that sounds really efficient. So all we do there is we set another new default argument of floating point 16 equal to a binary flag of true. And this will proceed very quickly, though apparently not as quickly as I can speak. And so now our training time is lower than we've seen before. So we're down to 15 seconds. Our previous record was 18 seconds. So now we're down to 15 seconds. And in addition, our memory has still stayed small. So we've managed to retain almost as small memory as we had before while getting a much faster training time. Nice. All right. And then we have dynamic padding and uniform length batching. This is our last little efficiency to talk about. So imagine that these are your 12 training points. So we have 12 different movie reviews, each with a different length. What we did initially is we set all of them to have padding that was equal to the largest one. Actually, we did something even less intelligent than that because I just set it to a large value, 1024, that I assumed without checking that all of our movie reviews would fit into. So here, this is even a little bit more intelligent where it's saying, what is our longest movie review? And let's use that as our cap. Dynamic padding is this idea that you only pad up to the largest document in that one batch. So you save on doing this compute, and look at on batch 3, we save all of this compute here, which is great. But dynamic padding with a sorted data set with this uniform length batching is even smarter. So this uniform length, it doesn't necessarily mean exactly the same length, even though uniform sounds like that. It just means about the same. And so that's related to this ranking. So we have uniform-ish length across all of the training data set points in a given batch. So if you were to shuffle between epochs, then I guess, yeah, you can't. Which actually, interestingly, with LLMs, the typical thing that you do is you use all of your training data once. You typically, this is a different kind of example where we have a relatively small amount of data set, but when you're talking about training an LLM for general purpose, when you're training it on billions of tokens, you typically run for one epoch. Nice, so let's see how that impacts our model. So this is a little bit more complex than the other changes because we have to change how we collate our data. But you've got this really convenient Hugging Face transformers method for doing that. And then we just recreate our training and our test data sets, repass those in, and then this is super fast. It's by far, look at that, 6 seconds, 7 seconds, and without increasing our memory usage. So clearly, this is the way to go. And over the course of all of these optimizations, we've made huge improvements. So we went from our vanilla training without all of these efficiencies. It was taking us 24 seconds and used up almost all of the memory on our GPU. And now it is running in a small fraction of the time, a quarter of the time, and only half of the memory usage. So all these changes make a big difference.
Well, for example, you have a batch, while short reviews are this move was great, right? So that's going to create a gradient where the model says, okay, well, short.
Oh yeah, I guess it would create a problem. Yeah, I guess that could potentially create a problem. Yeah, I hadn't thought about that. Assuming your batches aren't too small, and assuming that problem isn't like, if your label was predicting, if it was like really directly correlated with short review and long review, then you'd get into more of a problem. But yeah, that's a good catch. I hadn't thought about that, and it's a really good point to be aware of that. All right, last little thing I have in the notebook here for you is explainability. So I'm just going to empty the GPU cache here. We're not going to need it for this. And I'm not going to take time. We have too many other things to cover for me to go and explain how all of this is working in a lot of detail. But what Lime does is we can take a given data point. So specifically here, we're working with that same movie review that we were looking at earlier. And what Lime does is it sends that movie review, remember the one about the cogent story? It sends different samplings of it through the model. And by sending those different samples through, we can build up a sense of what tokens are more associated with a positive review versus a negative review. So it's finding that the word spend is really negatively associated, whereas experiment is really positively associated. So this starts to give you a sense. It allows you to understand your model a bit better and potentially explain things to your clients in some circumstances. The other big explainability library is SHAP, S-H-A-P. Cool. So we understand how to train models efficiently now, and we're familiar with the Hugging Face Transformers library for loading in our model and doing fine-tuning on whatever task we'd like it to. What are the open source ChatGPT-like LLMs that are available to us? These are quickly disseminating. So every week, there's a few big ones of these that make the headlines. The first one was Llama, which came from Meta. And this had GPT-3-like performance at a 13th of the size. So it's 13 billion model parameters, whereas GPT-3 itself is 175 billion. So it's a 13th of the size and had GPT-3-like behavior. Researchers from Stanford took those Llama model weights and fine-tuned them on a data set of 52,000 instruction response pairs that were created using GPT 3.5. So they used ChatGPT to say, here's an instruction. I mean, I think they even used it to create the instructions. So, create lots of this kind of instruction and then respond to those instructions. They created 52,000 of these pairs. They said how much it cost. It was less than $1,000. And they were able to use that to fine-tune Llama, similar to the kind of fine-tuning that I just showed you how to do, and get results that were GPT 3.5-like, which, as we saw, is a huge step change because it has that kind of RLHF feel. It's aligned with us, and we can get zero-shot results. Vicuña came along and started to approximate more like GPT-4. So they were quantitatively superior to Llama and Alpaca, and this evaluation was actually done by GPT-4 itself. So they used ShareGPT, which is a browser extension that you can get yourself for easily sharing cool ChatGPT conversations that you've had with your friends. And so some people opt for those conversations to be put into the public domain. So it created this data set of 70,000 ChatGPT conversations. Vicuña trained on those, and then they used GPT-4 to compare themselves. So they also started with the llama weights, so 13 billion parameters. And so they said, how did we compare? So that's what this chart is up in the top right-hand corner. How did Vicuña compare with Llama, with Alpaca, with Google's BARD, with GPT 3.5? And they asked GPT-4 to do that evaluation quantitatively. So give me a score out of 10. And so Vicuña beat Llama and Alpaca in almost all cases. On their test set of 80 cases, it was about the same as BARD, slightly better, and not as good as GPT 3.5 on their testing set. A big breakthrough in terms of what you can do with these open source LLMs that you can fit on a single GPU came with GPT-4All-J. And the reason why this was a big breakthrough is because it has a commercial use Apache license. So these previous architectures were based on Meta's Llama, and Meta did not allow commercial use. So with GPT-4All-J, all of a sudden, you could use these models freely, and they've fine-tuned GPT-4All-J. So they started with GPT-J, which is completely open source, Apache 2.0 licensed, and then they fine-tuned it on 800,000 open source instructions. I don't have for you a convenient benchmark of how well exactly it performs. This is comparable to the model that we started off today's training with, that we downloaded those quantized CPU weights and had it provide an explanation as to what an LLM is. That was using GPT-4All, which is actually not the commercial use one. That one was based on llama weights, but GPT-4All-J is commercial use friendly. Dolly 2.0 came out the same week as GPT-4All-J. It was released by Databricks. It also allows for commercial use. Interestingly, it's fine-tuned on human-generated instructions, 15,000 of them, by people who work at Databricks. And so this is another model that you can be considering playing with alongside GPT-4All-J. A week after that, Cerebras came out with their models, and so this is really interesting. So we were talking about a moment ago how we typically, with training these LLMs, we train through all of our training data once. And so a year ago, researchers at Google, they did an experiment where they experimented with lots of different data set sizes as well as lots of different model sizes. And what they determined from that experiment, doing like a grid search over all of these possibilities, they found this optimal ratio, which ends up working out to about a 20-to-1 ratio of training data to number of parameters in your model in order to get the optimal model training for a certain compute budget. Because what this means is you could actually, if you don't have that constraint of for a certain compute budget, you can just train for longer. You can always train for longer. You could train for a second epoch, and that would actually give you even better results. But if you're constrained by a certain budget, and you can say, okay, how much training data should I ideally use for a model of this size? Then the answer is that you should have 20 times. So if you have 1 billion parameters in your model, then you should train it for 1 epoch on 20 billion tokens. Got it? If you have a 2 billion parameter model, you should train it on 40 billion tokens. So these are what today are called the chinchilla scaling laws. And so what Cerebras did was they created a family of 7 models. They're shown here in this bottom right-hand chart. So 7 commercially usable models ranging from up to 13 billion parameters, which is comparable to Llama, Alpaca, Vicuña, and GPT-4All-J, but also going down to quite a bit smaller. And so the advantage of this is that they trained on way more data. They pre-trained on way more data. There's 2 steps here, right? There's the pre-training on all of the unstructured data that you use that I just described with this 20-to-1 ratio. And then after you're done that, you fine tune on the instructions. I can't remember exactly how they fine tuned, but the base model, the pre-training, used these 20-to-1 ratios, these scaling laws. And so it means that you can pick a model that's quite small, 100 million parameters, very tiny, will be very efficient, very quick to download. You could run it on a CPU, especially after you quantize it very quickly. And now you know that it's been optimally pre-trained with this 20-to-1 ratio. So that's great. It's a great starting point. So that was the cool thing about this Cerebrus GPT family. And then a week after that came Stable Diffusion with their stable LLM model. We already talked about this earlier when I was showing a Hugging Face example. The big thing that Stable Diffusion did here was they collated a bigger open source data set than we'd seen before. It has 1.5 trillion tokens, which means that if you want to spend the compute on it, you could be using this huge, vast data set to train for even longer than the Cerebrus folks did. They have released 3 billion and 7 billion parameter models already, and they have models up to 175 billion parameters planned. So there's lots of different ways that you might want to do your fine-tuning once you've downloaded the single GPU open source LLM of your choice. Because there's so many ways to do it, instead of me going through my own specific example, I'm just going to use Sinan Ozdemir's example, just kind of quickly talk you through his notebook here so that you're left with a clear sense of how you can be using it yourself. So we're using transformers, pandas, the Hugging Face datasets library. And what we're going to do here is we're going to use Distill GPT-2, which is an even smaller version of GPT-2. It's been distilled down. And we're going to fine-tune it on the Alpaca dataset. So remember, Alpaca was this Stanford group. They had their 52,000 instructions. So we load that dataset, and you can see examples of the training data of these instruction response pairs. And these first 5 examples, they only have an instruction. They don't also have this input populated. And so this extra input field, it's only used in a relatively small number of these circumstances, but it allows us to have an instruction as well as some other kind of input alongside the instruction. So identify the odd one out. Here are 3 examples, Twitter, Instagram, Telegram, which is the odd one out, and the correct response is Telegram. So you have 52,000 of these training examples, and you can see their lengths here. Most of them are relatively short. So we load in our Distill GPT-2 model, as well as its corresponding tokenizer. We pre-process the data by tokenizing it, converting it into our encodings for this particular architecture. And then we pre-process our Alpaca fine-tuning dataset as well. We split the dataset into a training and a test set so that we can compare performance as we train. You can see some examples of the dataset here. And then here we create an instance of our causal model. This is a generative model, so we want to use autoregression, which is causal language model. And then here is the code for actually doing the work. So for collating our data sets, and then we can train using these specific trainer arguments. So most of these are very similar to the kinds of arguments we've seen before. I don't think there's anything that I need to dig into particularly. I have some comments for the ones that might be not straightforward to explain, to understand. But fundamentally, the trainer is here. We instantiate it. And after training here, sorry, we haven't trained yet. We just evaluate first to get a benchmark as to how well we're doing. So we have our evaluation loss before we've done any training. Then we train here, and we can see how our training loss as well as our validation loss goes down over the epochs. So yeah, so it works, and I hope that gives you a sense of what you can be doing here. He also shows, we're going to go into some examples of this later as well, but saving the model into Hugging Face, and then you can be downloading the model yourself. So you could yourself download from Hugging Face this model that is now publicly available, and you could be using it with pipelines to very easily make use of this now publicly available, very small, open source LLM.
One thing I noticed, are there IP restrictions on using the OpenAI-derived like instruction datasets?
Yeah, so the question is, are there IP restrictions on using OpenAI datasets? So the terms of use with OpenAI state that you can't use OpenAI to create a model that competes with an OpenAI model. So I don't know what that means in terms of if you're creating a very niche model and using the OpenAI API to, I don't know, like it's not competing with OpenAI. I don't know. Like, can you? So I don't know where that. I'm not planning on finding out. Yeah. So yeah, depending on how. Yeah. So that's a good question for your attorney. I don't know. I am not a provider of legal advice. Sweet. So this has been useful, right? So already I think I've covered enough that you can be leaving here today with some pretty cool capabilities around downloading your own open source model and fine-tuning it to some proprietary task of whatever interests you, whatever would be useful to you. Now I'm going to get into PyTorch Lightning, which will make your job even easier. Because PyTorch Lightning is a PyTorch wrapper and extension that simplifies model training without losing flexibility. So you can adapt the PyTorch under the hood as much as you'd like. Key features of PyTorch Lightning include that it has a minimalist API, so you can quickly restructure your code from PyTorch into a Lightning module. That's all you need to do. It offers automatic optimizations. So those optimizations that we went over in the Hugging Face Transformers libraries, things like gradient accumulation, mixed precision training, and learning rate scheduling, which we didn't talk about, but this is how fast or how slow you should be training at any given point in your training. And so these kinds of optimizations are handled automatically by PyTorch Lightning. It has a built-in training loop. So if you were in my Intro to Deep Learning class yesterday, when we went from TensorFlow to PyTorch, all of a sudden we went from just having this nice, convenient train method in TensorFlow, or fit method in TensorFlow, to, in PyTorch, having to write out our epoch loop and then a nested loop inside of that does our batches. With PyTorch Lightning, we don't need to worry about that boilerplate anymore. With training, with validating, with testing, PyTorch does that automatically. It allows for distributed training out of the box. So you can have not just multiple GPUs on a single machine, but also multiple machines. It has a callback system that allows you to implement your own custom logic on things like checkpointing and logging. So again, more flexibility. It has integrations with all the most popular tools like TensorBoard and MLflow. And now you get to see what it's like yourself. So let's head into this fine-tune. So in this notebook, this is probably the single most substantial notebook in this training. I'm going to keep it as surface level as possible because we've only got half an hour left, and I still need to get to multi-GPU training, which is also a bit of a bear. So we've got our dependencies. We're using PyTorch for automatic differentiation. We're using transformers for our model, for our tokenizer and our training function. We're using PyTorch Lightning for easier training. So when I say training function here, I just mean literally this one little training method. It's specific to how we're scheduling our learning rate. We're using PyTorch Lightning for easier training. We're using TensorBoard, thanks to this built-in Jupyter Notebook magic. And later on in the notebook, I'm going to show you how to use parameter-efficient fine-tuning with something called low-rank adaptation, which dramatically speeds up how quickly you can be fine-tuning a model, particularly a large model. And then just a couple of system utilities. We've got some helper functions similar to what we had in the preceding notebook for getting GPU utilization metrics, as well as for generating our data set. So the GPT utilization method, it's the same as the one that we saw in the preceding notebook. And prior to any training, we again have very little memory being used. Remember, if you're running this for the first time, again, to change your runtime type to a GPU. and then you can select a model. So we're going to use T5 small because the task that we're going to do is pretty simple. And so T5 small only has 60 million parameters, which makes it a great choice for demo purposes here today. And you can read more about the other T5 model versions in Hugging Face here. So let's generate some of our data. And I'm not going to go over the data generation code. You can just trust that it works. You can actually see it right here. What it does is it creates a random sample of numbers. And our inputs into the model, we're going to fine tune it to take in integers as inputs. So 4477 is an example input from our training data set, from our first sample in our training data set. And we're going to teach this model to map that integer to the natural language representation, 4,477. We've created 1,000 training samples and 200 validation samples that consist of this kind of structure. Sean created a great streaming dataset method here, which I encourage you to use. So this is different from what we've been doing so far in this training. So previously in this training, with our custom fine-tuning, we've been loading in all of the data and pre-processing it all at once. Now here with the streaming dataset, it means that we're extensible to any dataset size because we're only going to load the data in when we need it. So in the interest of time, I'm not going to go through all the specifics of how we're like encoding and pre-processing the data here. You can go through that code on your own. But the key thing here is that it has this get item, which means that when we call down here for, say, a specific instance, so when I say I want the first instance of my training data, it will now go to this get item method and actually pull in the data and do all this pre-processing, all this encoding. Let's have a look at this, because this is something that you're going to see with a lot of LLMs. So input IDs we've already talked about. For T5 small, this is how the tokenizer converts it into the subword embeddings. And so there's a parameter here where we have this max length 16 parameter, which means that we have up to 16 tokens, and any of the token space that's not used gets represented as a 0. So this is our padding token. There's this cool other tensor here that we have called a sequence mask, which identifies which of the tokens actually has information in it. And the reason why this is useful is that the attention mechanism that we have in transformers is relatively computationally intensive. And by having the sequence mask, wherever we set it to 0, it means that we're not going to bother attending to those parts of the input. So we're going to save on compute. And then we have this target IDs, which is the same thing as here. It's just for our outputs. So input IDs is the subword tokens for our inputs, and then the target IDs is the same thing for our outputs. So unsurprisingly, so if you look at that very first example, it's unsurprising that we can represent 4477 in a very small number of subword tokens. But then when it comes to representing the output, it takes more tokens. So we have this longer output to learn. The idea of sequencing, of attention sequencing doesn't matter for the outputs. That's just for encoding. It's not for decoding. So there isn't the equivalent here. But we do have this additional label. This is an autoregressive model. What it's trying to learn is what the ideal next token is. And so what this is it's saying what the ideal next token is. So when you're in this position, what's the ideal next token? It's this. So 7863. Once you're in this position, what's the ideal next token? It's 662. So it's here, right? So this function here collates our individual data point tuples into batches. So it takes this tuple that was created by pre-processing our first training data point, and it just breaks it up into batches. So this function will break up our data points into batches of 4, so you have 4 input IDs, 4 sequence masks, and so on. Here is the Lightning training module. So we're seeing this for the first time. So we specify that we have a Lightning module. So going back to my slides, I was saying how the minimalist API, all we need to do is restructure our code from PyTorch into a Lightning module. So we have this PyTorch Lightning module. We're going to call it a T5 fine tuner. And some of the highlights of what's going on in here are we have our forward pass, where we pass in all of our training information into our model. We have training steps, so just making one step forward, doing one round of training with our training data, doing one round of training with our validation data. The difference here being that we don't do back prop during validation, we only do it during training. And so you specify these specific method names, and the PyTorch Lightning module knows what to do with those specific method names. So you don't have to provide all of the detail like we did in my class yesterday in PyTorch on all of the steps of the forward pass or all of the steps of a training step. It just handles that automatically. Data loaders provide clever optimizations like prefetching the next needed training data point on an additional worker. So this means that you can have one worker doing a forward pass or doing back prop, while another worker is saying, hey, I've got some excess capacity. What could I be doing? Oh, I could be fetching the next data point and pre-processing it. So you're taking advantage of these kinds of efficiencies. That's why it's lightning fast. Here you tell it how many samples to pre-fetch at any given time. That's a hyperparameter. And then there's an optimizer here. So we're using Atom, adaptive moment gradient descent, which was the same kind of optimizer that we were using in my training yesterday by the end of class. And there's some specific here like warm-up steps. This isn't something that we talked about and isn't super well known. This is something that we often see with LLMs, where we have very slow initial steps of training that allow our attention heads in our transformer architecture to warm up. I should have been running all this code while I was talking about it. I've got this for logging TensorBoard. I asked GPT-4 how to do that. And yeah, and then here we actually train the model. So we grab the pre-trained model, T5 small, and then our batch size is 256. Not 4, sorry. I must have gotten that from later in the notebook. And then so we pass in our training arguments, just like we did in Hugging Face. So what learning rate we would like to have, how many epochs are we training for, mini batch size, and then very simple syntax here for actually doing the training. We create a PyTorch Lightning model that with our Hugging Face model. So we use Hugging Face to create our specific instance and download that Hugging Face model, T5 small, and then we pass that as the first argument into our custom PyTorch Lightning class that we created here. So the first argument is the model. We pass in a Hugging Face model into PyTorch Lightning, as well as our arguments for our hyperparameters for training, our training data, and our validation data. Here we actually run the trainer, specifying our epochs, how often we want to log results. This defaults to 50, but I set it to 4 so that we could have something to show you guys right away. And once we have our instance of the trainer created, PyTorch Lightning trainer, here's a callback for the TensorBoard logger, by the way, forgot to mention that. Then we can run fit on it, and it actually starts fitting. So here we go, it finished training. After the 1 epoch of training on this very small amount of data that we asked it to do, we ended up having a training loss of 8.3, validation loss of 7.6, and you can see how much GPU space we're using, and you can see how with all of the optimizations that PyTorch Lightning takes into account, we're using up just a very small amount of memory, which is pretty cool. And it corresponds to a size of our model. So our model is pretty small here, 242 megs. And so that's what we're seeing stored in here. And so if you want to see this predicting on an individual data set, we haven't done very much training, so it's not going to be a very good model. But here's our first example in the validation data. So the first input is this, and the corresponding word is this. So we can look at what each of these individual validation points look like after we've converted them into their subwords. So again, we have our validation IDs and a validation mask, similar to what we saw with the training data. And we can now pass these validation data points, so the validation input IDs, as well as our mask, pass that into the generate method of our PyTorch Lightning model. And we specify that we don't want more than 16 tokens being passed out. And here we go. So it generated these subword tokens. Did it do a good job? We can now use the decode method of our tokenizer in our PyTorch Lightning model to actually output its prediction, and it isn't very good. But we've only fine-tuned for a few seconds on a very small amount of data. A quick thing to show you, in addition to training on the whole model, there's a really cool technique here called parameter efficient fine-tuning, which is also available from Hugging Face. You can read all about it in this repo here. And what this does is, in a nutshell, it allows us to insert matrices, additional new matrices, in strategic points throughout our big LLM. And we just fine-tune, we just train these strategically placed new matrices. We leave all of the rest of the LLM frozen. This helps avoid catastrophic forgetting, but it does, in some cases, actually allow us to even outperform fine-tuning on the whole architecture. So it's compute efficient. It avoids forgetting some things that the LLM was pre-trained to be able to do, and it can even give us more accurate results. So this code here shows how to do it. We use the low rank adaptation, which is a specific kind of PEFT. And so the arguments here are that we turn inference mode off when we're training. These are hyperparameters related to this specific low rank adaptation. So the lower that you make this R parameter, the fewer parameters you're going to have for training. Alpha relates to generalizability. I've seen people use 8 or 32. And then you have dropout, which is just like dropout for regular deep learning model training. And so now what we see here is that even though we have, in our whole model, we have 60.8 million parameters in T5 small, we have just 300,000 that we're now going to train. Oh, and I should also say thanks to Grant Baileveld in the back corner for teaching me about PEFT. Super cool technique here, where now we have, out of our whole big LLM, we're only going to have 0.5% that we actually train. And other than that, all the other training arguments stay the same. We've just set up our Hugging Face model to get the PEFT model. So we instantiate a new Hugging Face model, pass it through this get PEFT model function with the PEFT configurations, and we now have this PEFT configured model that we can pass into PyTorch Lightning the same as before, and it trains very, very quickly. Uses up a little bit more memory. Obviously, it's still not going to perform very well because we didn't train for very long. But just so you can see how it works, if you haven't used TensorBoard before, very easy to open up in even Google Colab. And when it opens up, you can use it to watch your model train over time. So you can watch epoch over epoch, how your training loss changes. So after this just quick epoch that we did, we have this one particular step. But if you were to continue training for more epochs, or you could watch it over steps, you can see this chart of your training loss, your validation loss changing over time, which is pretty cool right here in your Jupyter Notebook. Nice, so we're almost there. The last thing here that I want to make sure we get through is multiple GPU training. So with multiple GPU training, I have this set of steps which is available in my repo. So if you go to the NLP with LLMs repo into the instructions folder, there's a README there that explains how to do this. So you can create, this can be on your own cloud server, but for the purposes of anybody here being able to do it, I'm setting it up in Paperspace, which is a relatively expensive way of doing this. Sign in, select Core. So Gradient allows you to use Jupyter Notebooks. Core is actually just setting up a whole server. We can't do this in Google Colab, and we can't do it in Paperspace Gradient because you can't do multi-GPU training in a Jupyter Notebook. So we have to do this at the command line. So I have this machine that I already created here. I provided you with instructions for creating your own machine to have similar specs. So use ML in a box. The cheapest multi-GPU machine type will be fine for this problem. Pick a region that's closest to you. For authentication, set a password. I'll show you why in a second. And then in advanced options, set a static IP. Wait for the machine to boot. I have already done that so that we didn't have to wait for it. And then I can go into a command line interface like terminal. And you need to run this git clone to clone my repo, which will obviously grab all of my code into your server. I've already done that. And then there's Poetry, which handles all of our dependencies. If you haven't already installed Poetry on your machine, you can use this line of code to do it. Then change directory into my repo. So when you create your Paperspace machine, they'll provide you with an SSH URL as well as a password. And so you can use that to log into the machine. I'm also going to have this other one here for looking at GPUs. If you haven't run Poetry before, you'll have to run it. Then you can cd into the GitHub repo that you cloned. And then you just run Poetry install to get all of the requirements running. And I've already done that, so it's just telling me that there's nothing else to do. And then you use Poetry run to have Python run with all the dependencies that we specified in the Poetry file. So it's kind of like a Docker file. And then I'm running this code, which is this fine-tune multi-GPU code, which we can take a look at here. So it's a Python script. And it has all the same kind of functionality as we had in our single GPU file. So the T5 tuner in PyTorch Lightning, the streaming data set, and the only differences are here with our start training, where we have things like specifying mixed precision, specifying our GPU, and this deep speed stage 3 strategy. You can read more about it here, but what it's doing is it's sharding our model as well as our data onto however many devices we have, which on this machine that I set up in Paperspace is 2 GPUs. And so that's the main part of what's going on here. And so now it's running. So I have it running here in my cloud instance that I set up, and we can go into that cloud instance and run the NVIDIA SMI function to see that it's running on both GPUs. So it's using up 2,400 megabytes on both of my GPUs. And so that's allowing it to speed along very quickly. Once you have trained your model to your liking, so I'm just going to stop it here, but after it has completed training, there's a couple of lines of code here that I specify in the instructions that allow you to, if you uncomment these 2 lines of code in here, these 2 lines of code in the PyTorch Lightning start training method, if you uncomment those and then you run this Poetry run Hugging Face CLI login, it will push your model up into Hugging Face. And so Sean already ran this model for long enough, and he uploaded it to Hugging Face. So now you can go into Hugging Face, and you can type in integers, and it will download the model and compute. While it's downloading that model, I'm going to quickly show how you can actually do that also in a notebook. So I've got a notebook here for doing it at the command line. So I have this T5 inference notebook, which is the very last notebook for today's class. I'm not going to go into Colab because I still have a few minutes of stuff that I want to get through. But we import PyTorch and transformers to now use our very own model that we download. So we download the model from Hugging Face that he uploaded, and then we can use it to make predictions. So you can pass in any predictions that you want. -25 comes out as -25. So it worked. And it even works for these very long numbers into the millions. So there you go. That's fine tuning on multiple GPUs. It should also work in the UI if Hugging Face ever finishes loading it here. Just in terms of the rest of the slides here, there's stuff on considerations, like Lightning makes things easy, but you still might want to shrink your models through quantization, model pruning, or distillation. Those are various options available to you. In production, you want to be looking out for model drift. There's algorithms for detecting that drift and many commercial ML monitoring options that you'd want to consider if you have LLMs in production. There are major challenges today with LLMs, their large size being one of them, and there just being so many options out there for you. Encoded knowledge still today can be harmful or hallucinated, and you're vulnerable to malicious attacks from your users where they can try to figure out what your prompts are, and so therefore taking your IP. So yeah, transformers in PyTorch Lightning make model training, pre-training, fine-tuning, storage, and deployment easy. Abundant open source options provide opportunities for you to have proprietary and performant LLMs tailored to your needs. In this fast-moving space, there are, however, reputational and security risks. My final section here, which I'm just going to race through quickly, is on getting commercial value for LLMs. So how can we be supporting our other machine learning models with LLMs? We can be using it to label data in really extravagant ways. We can quantify our performance like we saw with Vicuña. We can be using it to compare our model as it trains over time or compare our model against other benchmarks. We can use it to augment our training data through things like back translation, synonym replacement, and wholesale generation of new natural language data. So what kinds of tasks should you be thinking about that can be replaced? Well, there's any kinds of repetitive tasks can be replaced, whereas creative tasks can be augmented with AI. So generating domain-specific copy, summarizing documents, we talked about lots of these examples. You should be using GPT-4 or Codex yourself for your code. And then also, you could be thinking about how you could be leveraging GPT-4 to be a better holistic thinker. So what ML models could you be deploying? How could you make your platform stickier? What data-driven feature should we build next? How can I increase revenue? These are the kinds of questions that you can be asking GPT-4 and providing it with a huge amount of context about your specific problems. This enables you to become a data product manager without any extra effort. All of a sudden, you're contributing more value to your company. You can be creative about leveraging existing LLM APIs, about fine-tuning your own, say, single GPU LLMs for proprietary task accuracy and efficiency, like I showed you how to do in today's training. And yeah, evaluating the performance of your models using these kinds of tools as well, like we saw with Vicuña. In addition to data scientists, you're going to need these kinds of people to have a successful data product. And these are the kinds of tools that I recommend, processes and specific tools that you can be using to be making the most of your data science team and collaboration together. The kinds of things that are going to be happening next with LLMs are that they're going to be smaller, less hallucinating, more real-time information, more modalities handled, better video generation, agents like AutoGPT that can perform very complex tasks by assigning subtasks to other GPT-4 agents. They're going to be domain-specific thanks to you working on them and embedded everywhere. And due to scaling limits, we're going to have to come up with new architectural ideas. And so because of all this, a year ago, if you had said to me, in our lifetime, will we have capabilities like we have today now with GPT-4? If you'd asked me that a year ago, if you explained the kinds of things that GPT-4 can do, I probably would have said to you a year ago, I don't know if we will have those capabilities in our lifetime. And now we have it today. So the speed at which this is moving is staggering. And it isn't until the last few weeks that I've been believing the hype around things like the singularity, but it is possible that we are in our lifetimes going to encounter abundance through interfacing with these ultra-intelligent machines. And I encourage you to think positively, optimistically. Obviously, there are risks that we need to overcome, and we could fill a 3-hour lecture with those kinds of risks and how we might want to overcome them. But think big about what you can be doing with the skill set that you have. As people in this room, you are some of the best positioned people on the planet to be thinking about how we can be using these new capabilities, these new AI capabilities that are staggering, and use them for good. And so it is possible that in our lifetimes we will have abundant energy. Some of the issues around nuclear fusion, a lot of the way that these reactors are set up it's plasma touching the walls of the reactor that causes a problem, but real-time AI systems that can use lasers to keep the plasma from touching the walls, it's AI that it will probably allow us to have fusion energy, maybe commercial reactors in the next decade. Abundant nutrition, extended lifespans, potentially reversing aging, education available to people, to anyone with a phone all over the world, freedom from violence, freedom of expression, ecological sustainability, cultural preservation, a sense of exploration in your life, and a sense of community and social connection. All of these things can be possible in our lifetime to every living being on the planet. It's insane. In conclusion, I introduced you to LLMs, the breadth of their capabilities, how to train and deploy them, and not just how to get commercial value, but how to get value for our whole society from LLMs. Further resources for facilitating this utopia that I've just envisioned for you. I have a 3-part Super Data Science podcast series on GPT-4, episode 666, on capability overviews, unleashing the beast here. 667 on harnessing those abilities commercially. 668 is on risks, so you can dig into those with an expert, a global expert on those, Jeremy Harris. If you want to understand more about transformers and GPT structures in general, Andre Karpathy has an amazing video that's been watched over 2 million times. Sinan Ozdemir, whose code I used a huge amount in this training, he has great O'Reilly video tutorials, live trainings, and a forthcoming book. Some of those chapters are already available in O'Reilly. Highly recommend Sinan Ozdemir for learning from on this stuff. A huge amount of what I taught you today, I learned from him. People from Hugging Face created an NLP with Transformers book that is already out and that is excellent. Ship Huyen has an amazing guide to ML ops, which is key for being able to handle these larger models. Educating yourself on how you can be better at ML ops is key to you being valuable as a data scientist as models get bigger and bigger and bigger. Vin Vashista has an amazing course on commercializing LLMs if you're interested in that piece of it, as well as a forthcoming book on the topic. And I'm hiring a director of data science if you want to be working on these problems with LLMs with Grant and me and Sean, who contributed a lot of the code for this, and Andrew, who's also here at the conference. If you want to work with us, we're looking for a director of data science who will actually, you should already know most of the content in this training, because we're looking for somebody that can be taking open source LLMs and fine-tuning them, and all the associated ML ops is ideally what we're looking for. You can follow through this link to get the full job description. It's about 3 pages. And yeah, so thank you very much for your time. Please do stay in touch.